In this video, I'll go through one of the fixed point iteration methods where we rearrange our equation into the form x equals g of x. We call it the g of x method for short. This method involves using an iterative formula. We start by rearranging our equation and we get x on one side and everything else, which will be a function of x, we call it g of x, on the right hand side. And this gives us what we call an iterative formula. So what we do, we pick an x value and we call it x0, and that will be an integer close to the root. We put it into this function and this will generate a new x value which we'll call x1. We then put x1 into the function and it generates a new value which we call x2. Now as we keep iterating, what happens is the x values get closer and closer to the root. So to start with, if we use the equation that's in the booklet that you've been given, then the equation we're looking at is x cubed minus 3x plus 1 equals 0. We start by rearranging this to leave x on one side and everything else on the other side. Now there's actually quite a few ways you can do this. I've used different colours for the x's, so hopefully you can trace what's going on. Here's one example where what I've done is to have x cubed plus 1 on one side and one of the red x's has gone over to the other side. So we'd have x cubed plus 1 is 3x and then just divide by 3. So x is x cubed plus 1 over 3. Now you might want to take a moment, pause the video and just check that you can see how the original equation here can be rearranged to leave one of the x's on one side and everything else on the other side of the equals sign. So there's a few different ways that you can do this. And what we end up with then is that if we plot y equals x and y equals g of x, where g of x is one of our functions here on the right hand side, then where they intersect should be at the same x value as values that satisfy the original equation f of x equals 0, because it's just a rearrangement. So any x which fitted here, so some number that when you cube it, minus 3 times that number and add 1 is 0, would also be a number that if you do the number cubed add 1 divided by 3, you get the number itself, and so on. So any time that we plot y equals x and y equals g of x, an x which is the intersection of those two graphs would also be an intersection of y equals x cubed minus 3x plus 1 and y equals 0, which is just the x-axis. Hopefully showing you that with the graphs will help it become a bit more clear. Now at first glance I can tell, yes, this is a bit of a complicated looking graph, but hopefully you'll be able to follow through what's going on. So we've got y equals f of x. This is the original cubic here. This is x cubed minus 3x plus 1, the red dotted line here. We've got y equals x, which is this straight blue line here, and then we've got y equals g of x. Now on this particular diagram I've used the x cubed plus 1 over 3 for my g of x. It turns out then it is just another cubic. Your g of x could be, well, there's all sorts of functions it could be. It could look a completely different shape to this. But a way you can check that you've done this correctly is what you should find is if you look at the x value, where f of x is 0, that should be the same as the x value, where g of x and x, so y equals g of x, this purple graph, and y equals x, the blue line there, where they intersect. So the x value of that intersection is the same as an x value of the root. This happens in all three places. So here we've got f of x is 0, here we've got y equals x and y equals g of x intersecting. And also over here there's f of x equals 0 and there's the intersection of y equals x and y equals g of x. So we'll only actually pick one of the rearrangements, but you might want to try a few of them in order to see which one makes the best picture and which one is nice and easy to calculate with. So have a play around with your own equation and different rearrangements of that equation to see which one you want to use in your coursework. All you have to do, once you've rearranged it and you've got x on one side and g of x on the other, your iterative formula is x r plus 1 on the left and then anywhere that you have an x on the right hand side of your equation, that will be xr, and then your xr value gets put into your g of x to produce the next value, which is the xr plus 1. Now, sometimes this method doesn't work. That's okay, because you do need an example of where the method fails to find the root in your coursework. So if it doesn't get you towards a root, that's okay. Just hang on to that and use it to show that the method sometimes doesn't work. So as I mentioned before, you always start with an integer near the root, which you can find by looking at the graph, and you put it into the iterative formula to find a value for x1, which is closer to the root. You put that into the formula to find x2, which is even closer to the root, and so on. I'll show you how to do this on Excel. Before looking at Excel, it's actually a good idea to use Autograph to draw a picture of this method working, and it will help you decide if this is one you want to use in your coursework. You might find that sometimes the diagrams don't work out very nicely, and you might want to just choose a different rearrangement, so a different g of x. What's happening though? In the equation that I've used, there was a root in between 0 and 1. So this is the root that I'm going to try to find. Now I could use 0 for my first x value, or I could use 1. I've chosen to use 1 as my value of x0. I can generate this picture on Autograph, and I'll show you how to do that later. But what we can see happening is that at x0 we have this value which gets put into g of x. So the y coordinate of g of x is here. We make that our new x coordinate. So if we have the place here where the x and y coordinates are the same, so it's on the line y equals x, then that's our new x coordinate x1. We're going to put that into y equals g of x. It gives us a new value, but that's going to become our new x value. So here it is, and that's x2. We put that into g of x, and that gives us a new value, and then that becomes our new x value, which is x3, and so on. On the diagram, you should have 4 labels like this, so from x0 up to x3, with either a staircase like this, or sometimes you end up with a cobweb diagram. Here's an example of the cobweb diagram. It's the same sort of thing, but this one isn't fully labelled just yet. But in this one, it's a different rearrangement this time, but we've still got the original curve. This is the y equals f of x. I'm not looking for the same root this time. That's the one I was looking for before, in between 0 and 1. I'm now looking for this one in between 1 and 2. In this diagram, I put in x0 was 2. It goes to the g of x to get a new value, and then that becomes the new x coordinate. So we see here it goes over to the line y equals x. We put it into g of x, which gives us a new value. That becomes our x coordinate. This time, instead of making a staircase, we get this kind of a cobweb design as it converges towards the root. So here's how to do this in Autograph. Hopefully you know how to draw y equals f of x in Autograph. So in this case that's the red one here. Y equals x, the blue line, and y equals g of x, which is one of the rearrangements that I've found, and in this case it's the purple one here. So firstly, I need to highlight the y equals x and y equals g of x. I do this by clicking on both of them and holding down the shift key. When I've done that, what I should find is that they both go black. That means they're both highlighted. When I've done that, if I right click, I can do that anywhere, I will get this box that comes up which offers various things, and second from the bottom there it says x equals g of x iteration. So I click on that. That will bring up a box which I can see over here, and it will ask me for an x0 value. So I chose to use x0 is 1. You then click on this button, and once you've clicked it once you get what you can see here. This is the first iteration, and then you just keep on clicking on this button several times, and each time you click you'll get another piece of the staircase or piece of the cobweb as you go along. You can zoom in so that you can see enough stairs or enough bits of the cobweb that you'll be able to label x0, x1, x2, x3 on your diagram. Here's an example of the same f of x, but I was trying to find this root which was in between 1 and 2. So I thought I could use 2 as my starting integer. So I tried to do that. I put 2 in as the starting integer and I started pressing this button to see what would happen. But this time the x value goes to g of x, back to x, y equals x, back into g of x, and it seems to be about to disappear off the page here. So rather than converging towards this root, it's actually diverging away. So I might want to use this in my coursework as an example of where the method fails to find the root. Okay, so let's take a look at what happens in Excel. So we have got to type in x0, x1, x2 and so on. I'll show you how to make them look like that in a moment. So next to x0 we type in the integer that's close to the root. So I type in 1 in cell B1. Now the iterative formula goes underneath that. So my iterative formula, I'm going to need x cubed plus 1 over 3. So for x, I'll click on the cell above and then cubed, I use the hat 3 plus 1. I need to be careful here with brackets around that whole numerator and divide by 3. Now I just type that in the once and then I click and drag and that should fill in all of the cells with the same formula for me. So each time it uses the cell above to calculate the value. So this is what happens on the table. My 1 was the one that I entered, then that goes into the formula. So 1 cubed would be 1, add 1, that's 2 over 3. So I've got 2/3. There it is, hopefully you recognise that that's 2/3. Then it would do 2/3 cubed add 1, all divided by 3, which ends up being about 0.43, and then it puts that into the formula and so on. What we see here is it's started to look like it's repeated some values, and I've highlighted those just to make it clear that it's the same value. And I need to check this though. Perhaps if I kept the click and drag going, it might change and perhaps it will become 34729. It looks like the values are going down. I need to be sure that that's stopped and it's not going to change and it has actually got that root with the error bounds that we used in the other parts of the coursework. So I need to do a change of sign check here. So what I'm going to do is just go 0.5 zeros and a 5 above and below that value. So that gives me the values of 347,295 and 0.347305. And one of them is positive, one of them is negative, so I know the root is in between those values. So I can be quite happy that I've got my root with my maximum error, which is the same as I used in the other part of the coursework. Now, when it fails to find the root, this is where the staircase was diverging away. What will happen? I put in my x0 value, here I've put in 2, and then here, what we've got here, 2 cubed add 1 divided by 3, so that's 8 add 1 is 9, divided by 3 is 3, so x1 is 3. Now my root was in between 1 and 2, but instead of getting closer to the root, it's gone to 3, which is further away from the root. And then when I do 3 cubed add 1 all divided by 3, I get 9 1/3, which is even further away from the root. And if I keep doing that, it gets further and further away from the root. In fact, all these hashes have appeared. That's just because the value's got too many digits to actually fit in the cell width, so I'd have to expand the cell to be able to see what those numbers are. They're pretty big numbers. And then it starts saying hash num exclamation mark. Now that's an error message just letting me know that those values are actually too large for Excel to calculate with. So that's what I'd need to show and explain when I'm talking about the method failing to find the root. So here I'm just showing in Excel how you can make these values x0, x1, x2 and so on so that it looks good and you label all your x values. All I do is I type x0 into cell A1. I then click on the font tab and this little arrow at the bottom of where it says font, and it brings up this box, and one of the options there is subscript. Now actually I should have said before doing that, what I do is I just highlight just the 0 because it's only the 0 that I want to become the subscript, not the x as well. So when I've highlighted the 0, I click on this little arrow, I get the box up, go for subscript, and I click OK. That will then look like this cell here with A1. Then if I just go to the bottom right hand corner and click and drag, it will automatically keep doing these going up x1, x2, x3 and so on. When I'm using Word to write about this method, I'll want to put this iterative formula, so I'll need to be able to write this and make it look mathematically correct. Now the way I'll do this, in Word I'll go to Insert, which is the second tab from the left next to Home, and then over towards the right hand side of the page at the top it says Equation, and it's got a little symbol pi. It'll ask me if I want to enter a new equation at the bottom of the list when I've clicked that. I then can use these various options to make everything look the way I want it to. So for example, this bit here with xr cubed, I'll use this one. So I'll put the x here, the r, and then the 3 for the cubed. For this bit, x r plus 1, I'll use this part over here. I'll put x and r plus 1. If I click on the fractions button, that will enable me the option of having a fraction, so I can press that and make sure that I get part of it in the numerator and then the 3 here in the denominator. In both the case where the method helps me find a root of an equation and in the case where the method fails to find a root of an equation, I have to explain about what's going on here. And there's this rule that we have, that it will be successful in finding the root if we have that the gradient of g of x, so g dash x, is in between -1 and 1. So that means my g of x will be less steep than the line y equals x, or less steep than y equals minus x if it's going downhill at that point. If we don't have that, then the method will fail to find the root. So if the gradient of g of x is not in between -1 and 1, so it does not satisfy this, then it will fail to find the root. So I need to mention this within the coursework. Let's have a look at that diagram from before. Sorry, again, it's the cluttered one, but let's just have a look at this. Now actually, looking at it straight away, I can tell for this particular g of x where it will find the root and where it won't. So over here, this is the one that I used an example and we got the staircase and it found the root. This g of x is clearly not as steep as y equals x. It's got a gradient that's less than 1, and it's a positive gradient, so it's certainly in between -1 and 1. So here the method worked and we found this root. The one where it diverged though, when x is 2, here's my g of x. It's clearly much steeper than y equals x. The gradient here is definitely bigger than 1, so it's not in between -1 and 1. So this particular g of x won't help me find this root using a starting point of 2, because here near the root, my g of x is steeper than y equals x. The same sort of thing would happen over here. If I tried to find this root, the one that's in between -1 and -2, my g of x is much steeper than my y equals x. The gradient of this g of x here is bigger than 1, so it's not satisfying this inequality. I'm not going to be able to find the root. What I was doing just there was actually this method. I was comparing the steepness of the curve y equals g of x near the root with the line y equals x. Or if it had have been with a negative gradient going downhill, I could have compared it to the steepness of y equals minus x. There are other ways I can be even more clear about this. One is to use the gradient function, y equals g dash x, to find the gradient of g of x near the root. So here we go. Here's our root. Here's y equals g of x, and this green one is plotting y equals g dash of x. So what that means, the y coordinate of the green one tells me the value of the gradient at that point. So at the root, there's my root at that intersection, or I could say there's my root where f of x is 0. If I look at the value of the gradient, so the y coordinate here looks like about 0.1, just over 0.1. Now 0.1 is in between -1 and 1, so the method has worked here. There's another way I can do this as well. What I could do is draw a tangent to the curve. So this is the same route. So I've got my f of x is 0 down here. Here's my staircase, here's my g of x, and my y equals x. And I've actually drawn the tangent to g of x. Now I can do that by putting a point on the curve and right-clicking and saying add tangent, and it will draw the tangent for me on autograph. Autograph will give me the equation of that tangent. In this case, it turns out the equation of the tangent there was y equals 0.16x plus 0.2907, the key thing being that the gradient has come out to be 0.16. Now that's in between -1 and 1, which is what we wanted. So, in the coursework guide, it tells you all the steps you need to do. Make sure that you follow them carefully. Notice that you're stating the equation you're trying to find a root of. You're not solving the equation, you're just finding one of the roots. Make it very clear what you're doing and make sure this is a different equation from the one you used for decimal search, and it'll be different from what you use for your Newton-Raphson method. And you need to show how you've rearranged it. You need to state the iterative formula that you're using. That's the one with the subscripts with the r+1s and the r's in it. You need to show a graph with your f of x, your g of x, and the line y equals x all on the one graph. You need to show your calculations. Make it very clear what your x0 value is, so the integer near the root. And you'll need a zoomed in graph like the one I used with the labels from x0 to x3, and that will have a staircase or a cobweb on it. You need to describe how the method works, so talk about how the iterations are performed and how the XR values converge to the root. To do this explanation, you'll want to use your Excel table and your zoomed in graph illustration. You then need to do your check for a change of sign to confirm that you've got your root and put the error bounds very clearly here. There are marks for having the error bounds on this. You need to confirm that the value of the gradient of g of x, so g dash x, near the root is between -1 and 1. So there's various ways of doing that, which are explained in the coursework booklet, and I went over a couple of them just before. So in this part then, you've got writing about what you're doing. You've got two tables from Excel. There's the one where you do the iterative method, and there's the one where you do the change of sign check to make sure that you've got your value correct with your error bounds. 3 graphs from autograph. So that's one graph displaying your f of x with your g of x on it. There's one graph which is zoomed in showing your x0, x1, x2, x3 clearly labelled, and there's one graph where you talk about the gradient of g of x. You then also need to do all of that again, apart from the change of sign check, for a case where it doesn't work. So go through all of that. Be very careful, it has to be the same equation that you're trying to find a root of. It doesn't have to be the same rearrangement. So you can have a different function g of x, but your original equation f of x is 0 has to be the same as the one you've used where you did find the root. And so in this section, you're writing all about it. You show your calculations that show that the method fails to find the root, it diverges away. You have 3 graphs. You've got the graph illustrating your f of x and your g of x that you're using in this particular section. You've got your graph which is annotated with the staircase or the cobweb diverging away from the root, and you've got the graph where you talk about the gradient of g of x. And here we see the mark scheme. So all of that work can get you up to 4 marks. Check that you do everything that it says. So you might notice it says root of a third equation. They happen to put the Newton-Raphson bit before this. It doesn't matter that we do this before Newton-Raphson. So it's a different equation from before. And you use a rearrangement to successfully find a root. You talk about how this converges. You demonstrate graphically, so that's your zoomed in and annotated graph. You discuss the gradient, so that's writing about it and drawing a tangent or drawing the gradient function or comparing the gradient of g of x with y equals x. So that's all in there with a diagram. You then do the same equation and you show the method failing to converge with all the illustrations and everything that goes with it, and it's demonstrated graphically and the magnitude of g-x is discussed, so that's covering everything there. Basically, if you follow the steps 1 to 10 very carefully, you should do everything you need to do to gain those 4 marks for this section of the coursework.